We've proved the classification theorem, but there are a few loose ends in my exposition of that proof, and I want to talk about some of these. In the last 3 lectures. And hopefully this will give you a glimpse of kind of what would be next. So here's my kind of rough plan for these lectures, just so you get a clue where I'm going. So today I'm going to give you a glimpse of representation theory. So this is the next very substantial and beautiful topic that should be developed in this story. So I'm going to do enough of this so that I can discuss the Weyl dimension formula, which is needed in the proof of that tricky lemma. From lecture 9.2. So that was an important ingredient in the approach that I showed you. Okay, so I'm not going to prove any of this. I'm just going to state some results from representation theory, and your next job should be to go through the proofs of all of those results. So that's today, and then I'm going to talk a bit more about exponentiating. So that was the cunning trick, the interesting place in the proof of Serre's theorem in lecture 9.3, and that definitely needs more discussion, because I didn't give you enough detail there to exactly follow the argument. And then finally I'm going to explain how to construct semisimple algebraic groups. Starting from semisimple Lie algebras. So that'll be the last lecture, and so I'm kind of going back to algebraic groups finally and showing that actually, given these semisimple Lie algebras, which are rather explicit objects actually, I mean, we've constructed them using the Serre presentation, but there are lots of other absolutely explicit and concrete constructions of semisimple Lie algebras, and I'll show you how you get the groups back again out of them. Okay, so that's the plan. So today I'm going to give you this glimpse of representation theory. So let's just remember what we've done for SL2. We've actually done this rather completely. And that was actually the key ingredient in our construction of root systems out of semisimple Lie algebras. It explains most of what, all of that stuff about alpha strings through beta and so on. That all boiled down to this understanding of representations of SL2. So what did we show about that? We showed that every finite-dimensional SL2 module is completely reducible. We showed that the irreducible ones amongst the finite-dimensional ones up to isomorphism, labeled by their highest weights, which in that story was just some natural number. So we wrote L of n for the irreducible of highest weight n, and I gave you a construction. It was just the nth symmetric power of the natural two-dimensional representation. We had this great picture for it given by these little strings. which I've drawn many times. So the highest weight is n, and then you go down in twos, n minus 4, 2 minus n, and minus n. And the f's pull you down those strings, and the e's pull you up. So this is the highest weight, the lowest weight. So the labels here are the h eigenvalues of a basis, and I always remember I always use the word weights. And what else do we know? We know that the dimension of L of n is n plus 1, and we know that the element h in our standard basis for SL2, our standard SL2 triple, we know that h acts diagonalizably on any finite dimensional representation. Oh, maybe the final thing I should write down is the Clebsch-Gordon formula. If you take two finite dimensional irreducibles, we know how to decompose their tensor product. How shall I N O P, maybe P? So you sum from P going from n minus m to n plus m, with P being congruent to n mod 2. Congruent to n plus m mod 2, I should write there. So this is the Clebsch-Gordon formula. And I think that's on one of the homeworks. Homework 5, question 1. And maybe I draw the proof of Clebsch-Gordon because it's kind of an important one. So you have n along here and you have m along here. You kind of drew this rectangle. I think I did a special case in class, and then I kind of went around the northeast corner of that rectangle. That was an SL2 string in the tensor product. It went kind of like that. So that's kind of Clebsch-Gordon. So when I draw that weird rectangle and I go around the northeast rims and I say Clebsch-Gordon, you should think of that proof of from that homework, where you just look at the weights and you pick the maximal weight and you subtract that SL2 string, and then you pick the next weight that's left and subtract, and so on, and we ended up with that picture. Okay, so all of these facts that we've done for SL2, the point is to extend everything to a general semisimple Lie algebra G. So let's now just let G be a finite dimensional semisimple Lie algebra. In fact, I may as well just assume that it's the one given by the Serre presentation. So C here is a Cartan matrix. That's kind of handy, right? Because then it comes with this nice set of named generators, EI, HI, FI, I in I, with the Serre presentation. So we've got R sitting inside E, which is its root system. Delta for the simple roots. Sitting inside there, we've got, so that's the base. And then we've got our maximal tall subalgebra. And we've got our triangular decomposition. G is n minus direct sum t, direct sum n plus. So this guy is generated by the FIs, this guy is generated by the EIs. And let me see, I also want to let B be T direct sum n plus, that's the Borel subalgebra. So that corresponds to the positive roots inside the root system, right? So all of these things depend on this choice of base. It gives us this positive roots. It gives us triangular decomposition. Everything that you do in this subject depends on that choice. Okay, so we know quite a lot already about the representation theory of this G. We know that any element H in our maximal toral subalgebra is semisimple because it acts semi-simply on the adjoint representation. Hence it acts semi-simply on any finite dimensional representation. Of G. So that was our Jordan decomposition, which we worked hard for. And so as T is abelian, remember commuting diagonalizable linear maps are simultaneously diagonalizable. That means that any V in rep G decomposes, as V is the direct sum of all lambda in T star V lambda. This is our usual guy. This is the lambda weight space. That's all vectors in V, such that HV is lambda of HV for all H in our maximal toral subalgebra. Okay, so any finite dimensional representation decomposes as a direct sum of weight spaces. We know that already by Jordan decomposition. And we know that any finite dimensional representation is completely reducible. We've proved Weyl's theorem on complete reducibility already. Okay, so that's already two analogues of the facts I wrote down for SL2, which we've already established. Okay, so let's take some weight lambda in T star. I'm going to define a highest weight module of highest weight. Let me just write HW as a shorthand of highest weight lambda is a G module. Remember, that's the same thing as a module over the universal enveloping algebra. It's a G module generated by a non-zero highest weight vector. I'll always use V plus, I think, which should be a vector of weight lambda. It means a vector in the lambda weight space. Okay, so highest weight modules, highest weight vectors. Okay, so I haven't defined anything yet, have I? So highest weight vector of weight lambda means that all of the EI V plus is 0. And HI V plus is lambda of HI V plus. Yeah, put the formula over there. Or I could write this in a slightly more fancy way. N plus V plus is 0, and HV plus is lambda of HV plus for all H in H. Okay, so it's a vector in the lambda weight space, and this positive part, N plus, because of our work on the Sayre presentation, we know that N plus is actually generated by the EIs. That's all the positive root spaces of G. That kills V plus. So that's definition of a highest weight vector right there. So we kind of had that definition when we were doing SL2 in a special case. There's a universal such module, which which is the Verma module, m of lambda. So we constructed Verma modules for SL2, but so you can construct them in general. So you take C lambda. So this is the one-dimensional B module. So B now is this Borel subalgebra generated by a vector satisfying all that stuff. So B is just generated by the EIs and the HIs. The EIs act as 0, the HIs act as weight lambda. Okay, so that's C lambda. I'm thinking of that as a B module, and then you induce. So you tensor it up over the universal enveloping algebra of B with the universal enveloping algebra of G. It's the same construction as we did for SL2, actually, but we've got this triangular decomposition, so it makes sense now. Okay, so it's easy to see that if you let V plus be kind of 1 tensor 1 in here, this is the highest weight vector, and that gives you the, in fact the m of lambda has an easy basis because U of G is a free right U of B module on basis, we see you have to look at these f's, f beta 1 to the m1 all the way up to f beta n to the mn, where beta 1 up to beta n are the positive roots enumerated in some way, and f beta is kind of one of the standard basis vector for the minus beta root space. So remember we picked a kind of a standard basis E beta, H beta, F beta for each root. So you could take that, or I mean G minus beta is just one dimensional. It doesn't matter what F beta is so long as it spans G minus beta. Okay, so these monomials in the F's, they give a basis for U of G as a free right U of B module. That's just the PBW theorem. And so because of that, those monomials give a basis for the Verma module. So although it's infinite dimensional, it's completely under control in some sense. You have this basis and you understand, for example, it's diagonalizable with respect to t, you understand all the weights of it, so you kind of have a good control over this Verma module. And any highest weight module of highest weight lambda is going to be a quotient of m of lambda, just because m of lambda is an induced module, so just using Frobenius reciprocity, adjointness of tensor and Hom, you'll get that fact. So okay, there's the Verma module, that's the universal highest weight module of highest weight lambda. And then you have to do a little bit of work, and I'm not proving these things. This is the next step in representation theory. You show that m of lambda has a unique irreducible quotient, which you denote L of lambda. It'll usually be infinite dimensional at L of lambda. Generically, it'll be irreducible. And then any irreducible highest weight module of highest weight lambda is isomorphic to that L of lambda, right? So these guys, these L of lambdas, as lambda ranges over all of the space T star, these give all the irreducible highest weight modules up to isomorphism. So those aren't difficult things to prove, but I'm not giving any detail here. That's kind of the next piece of work that you should do. Any finite dimensional irreducible G module is obviously a highest weight module. That's obvious because there's just it's finite dimensional, so you just pick some non-zero vector in a weight space, and if it's killed by all the EI's, it's a highest weight vector and it generates because it's an irreducible module. Otherwise, you just apply some EI, it adds alpha I to the weight, and you keep going, and because it's finite dimensional, you must find some non-zero vector killed by all the EI's in this way, and then that the weight of that will be the highest weight of this guy, and using the universal property of m of lambda, you'll see that this guy is isomorphic to one of these L of lambda. So then it becomes the question of determining when L of lambda is finite dimensional, and exactly those lambdas, they give you the highest weights of the finite dimensional irreducible representations of G. So this is the important step, determining which L of lambdas are finite dimensional, and the answer is that it's finite dimensional if and only if lambda is what's called a dominant weight. So this becomes the next important notion, dominant weight. And so let me see, I've got to tell you this. So let's see. In one direction, this is really easy. If L of lambda is finite dimensional, what you do is you consider SI, the SL2, as EI on V plus, the highest weight vector in that L of lambda is 0, and HIV plus is, let me see, that's going to be lambda of HIV plus. Now, it must generate this vector V plus over this SL2. It must generate some finite dimensional irreducible SL2 module, and from our SL2 theory, we know that the highest weights of those are natural numbers. So you deduce that lambda of HI, if you prefer, you write that as lambda alpha I check, it's just the same thing, is a natural number. This is for all I in I. And that's the definition of dominant weight. Let's put a little box around that. There we go. So right there, that's the definition of dominant weight. And so I've just proved that direction. That's super easy. That's just representation theory of SL2. But this direction, this is quite hard, and it needs some new ideas to prove that if lambda is a dominant weight, then that unique irreducible quotient L of lambda of the Verma module is finite dimensional. So that's the classification, the extending our classification for SL2 when they were labeled by their highest weights, which were natural numbers. In general, the finite dimensional irreducible representations are labeled by their highest weights in this new sense, and those highest weights are dominant weights. So there's a little bit of notation here. So you let pi 1 up to pi L. So this is a funny LaTeX symbol. This is actually, it's a pi. In LaTeX, this is var pi. So it's a pi. You always see it and everyone calls it an omega, but it's a fancy pi. So pi 1 up to pi L. I think it's pi for poids. These are the weights. So let this be the dual basis to the co-roots. Okay, so this is another basis for the Euclidean space E over the real numbers, or it's a basis for T star over the complex numbers, depending where you're working. And then you let P be the set of all lambda in T star such that lambda alpha I check is a natural number for all I going from 1 up to L. So this is called the weight lattice. So it's simply, I wrote n, I meant z there, I apologize for that, is an integer. So this is just the z span of this basis, z pi 1, z pi l. And then you let p plus be the lambda in T star such that lambda alpha I check is a natural number for I going from 1 up to L. So this is just the kind of positive cone in here. So the n span, the non-negative sums of these fundamental, of these omega i's. And so I just used the word, so I better write it down. The pi i's are called the fundamental weights. Elements of P plus are called dominant weights. And they label the highest weights of the finite-dimensional irreducible representations of G. Okay, so this labeling, it depends on the choice of Borel subalgebra and maximal Toral subalgebra. So our choice of root system and base, everything depends on that. But then this becomes the discrete set, this set P plus of dominant weights. So n linear combinations of the fundamental weights that label the irreducible representations. Let's just think what that's saying for SL2, because it's a bit of a stretch to get here. So for SL2, well, the root system is just plus or minus alpha, right? So the base is just alpha. There's only one positive root, so that's the simple root. The Euclidean space E of that root system is just one-dimensional, spanned by alpha or by alpha check. And of course, alpha check is 2. So if you define pi to be the dual basis to the co-roots, right? So omega of alpha check is 1, i.e. Omega is just half alpha. Did I miss writing a 2 there? I did. Okay, so there's only one fundamental weight in SL2. It's a rank 1 root system. It's called pi. It's a half alpha. And I often call it omega by mistake because it looks like an omega to me. And then this set P plus, so that's n omega. And so what we've now got in this general setup is we've got L of n omega for n a natural number. So this has got this V plus, where HV plus, it's n omega of HV plus, but that's the same as n omega alpha check. Remember, H corresponds to the co-root alpha check V plus, but omega alpha check's 1, so that's NV plus. Oh, so that's exactly the same as what we were just saying. We were just saying n before for that highest weight. So that's the L of n from before. Okay, so that in SL2, the only difference to what we were doing before is that you have this fundamental weight omega, and instead of just writing natural number n, I should have been writing n omega, so that that's actually a weight inside H star, inside T star. Okay, so nothing really going on there. But in general, you're going to have these fundamental weights, these omega i's, and then for a lambda in P plus, so that's just the data of L natural numbers. AI will be lambda alpha I check, or if you prefer to write, I think it's more natural, lambda of HI. You have L of lambda, the corresponding finite dimensional irreducible representation. Okay, so that's talking about the classification of finite dimensional irreducible representations. And then things get kind of really fun. You have something called the Weil character formula, which I'm not going to even state for you. It's an awesome theorem and a beautiful proof. It's one of the highlights of the whole story. So this tells you the dimensions of L of lambda mu for one of these dominant weights and any mu in T star. Right? So this is the mu weight space of L of lambda. So this tells you the dimensions of all of these. That's called the character of L of lambda. So that generalizes what we knew for SL2 when we knew the eigenvalues of H on a basis. Now you know the weights of a basis. That's exactly what the Weil character formula tells you. Actually, it's easy to see that all mu, so L of lambda mu is non-zero, are of the form lambda minus some sum of mi beta i's. Just for the alphas actually, mi alpha I with the mi's being natural numbers. That's true already for the Verma module because of that PBW basis. Okay, so somehow this lambda is the sort of biggest one, and all the other weights they're obtained from lambda by subtracting simple roots. So from that it immediately follows actually that the only mu's that can appear, they're actually in the whole of P, the whole weight lattice. So we're already down to this discrete set P inside our Euclidean space as the possible weights. From the Weil character formula, you see exactly which mu have L of lambda mu non-zero. I'm going to denote this by, I'm just going to write P of lambda for this. So it's certainly a subset of the weight lattice P, and in fact it contains Q. So P is this weight lattice that I've defined before, the set of all lambda in T star such that lambda alpha check is an integer for all I, or z pi 1 direct sum z pi L. Q I haven't defined before. This is the root lattice. So that's z alpha 1 direct sum z alpha L. That's generated by the simple roots. So then once you've got the Weil character formula, you can also get a formula for the dimension of these finite dimensional irreducibles. So lambda is a dominant weight, and this is very simple. I'm just writing it down, the Weil dimension formula, and then I'm going to do an example. There it is. So you take the product over all positive roots of these inner products, lambda plus rho alpha check, and then you divide by rho alpha check. And rho here, we've seen this before, when we were developing the theory of root systems, half the sum of the positive roots was rather useful. And the defining property of rho is that actually rho alpha I check is 1 for all I. So actually now we have the fundamental weights around. Rho is just the sum, pi 1, pi 2, up to pi L. Is the sum of the fundamental weights. So let's see, I just wanted to, so this lets you calculate the dimensions of all of the finite dimensional irreducible representations. So I thought I'd do an example. Let's do an example with G2. I mean, one thing you see right away from this, right, is that if you have lambda that's not 0, a dominant weight, and if dim L of lambda is kind of is minimal, well, you'd better have that actually your lambda is pretty small. It'd better just be a one of these pi i's for some I. So I'm thinking about that table that I had in lecture 9.2 when I listed the dimensions of the minimal dimensions of the non-trivial irreducible representations. And that's just computed using this Weyl dimension formula. You're looking for the non-zero lambdas so that the dimension of L of lambda according to that formula is minimal. So right away from the nature of the formula, you see you better just take lambda. If it's not 0, it better just be 1 fundamental weight. And then you have to think about which I it is in each case. But let's just do G2. So where was our G2 root system? G2 was this thinking diagram, and I labeled them this way. And can I try and draw the root system? Let's have a go. So you have to draw your two nested equilateral triangles. Then there's the origin, and then here are all the roots. So that would be alpha 1, alpha 2. We just put the positive roots in. So this is alpha 1 plus alpha 2, 2 alpha 1 plus alpha 2, 3 alpha 1 plus alpha 2, and 3 alpha 1 plus 2 alpha 2. There's the longest root. And let's see if we can calculate the dimension of L of pi 1 and L of pi 2, because one of them is the minimal dimension. Let's do pi 1. So what have I got to do? I've got to take pi 1, so pi 1 plus rho is 2 pi 1 plus pi 2 alpha check over pi 1 plus pi 2 alpha check. I've got to take the product of those over all positive roots. And so I've got the positive roots listed in front of me. So on the denominator, I've just got to sum up the coefficients. So I'm just going to read them this way. And I'm just summing up the coefficients in each one. So it's 1 times 2 times 5 times 3 times 4 times 1. Or I've got to do twice the alpha 1 coefficient plus the alpha 2 coefficient. So there's going to be 1 times 3 times 8 times 5 times 7 times 2. And this works out to be, let me see if I can cancel a little bit, 2 4s, 5, 3, 14. In fact, this is the adjoint representation. Right, 14 is the rank plus the number of roots. There are 1, 2, 3, 4, 5, 6 positive roots, so 12 roots. So yeah, the adjoint representation is dimension 14. And let's do omega 2. So for omega 2, it's almost the same, except that I'm taking the alpha 1 coefficient and twice the alpha 2 coefficient in this sum. So the denominator is going to be the same. And then the numerator, so I'm going through my roots, I take twice the alpha 2 coefficient. Four and 5 and 1. So let's see if I can cancel some stuff. The 5 goes, the 4 goes, the 2 go, the 3's go, the 2's go. That's 7. So this will be the minimal dimension. And that is indeed the number that was in the table in lecture 9.2. Okay, so that's just kind of a glimpse of how once you've proved the Weyl dimension formula, and that's something that literally just depends on knowing the root system, knowing the Cartan matrix used to build your G, you can read off the dimensions. In particular, you can calculate this minimal dimension. That was the invariant that I needed when I was proving conjugacy and isomorphism theorems before. So I've kind of rapidly gone through just stating some of the kind of beauty of representation theory of these semisimple Lie algebras. I think I've got analogues of pretty much everything, except I haven't talked about tensor products. So for SL2, that was Klebsch-Gordon. And that's kind of a beautiful story in its own right. If you take two dominant weights, you ought to be able to take L of lambda and L of mu and tensor them together, and by complete reducibility, that'll decompose as a direct sum of some L of mu's to some multiplicity and it's rather interesting, these numbers. They're rather rich, and there's lots of different approaches to calculating these multiplicities from all sorts of points of view, geometric or combinatorial. My favorite way to calculate the C lambda mu news goes via the theory of crystals. So this is something much more recent than everything else I've been talking about. So this is developed by Kashiwara in about 1991, I think. And it's a very beautiful combinatorial machine for encoding the structure of these finite-dimensional irreducible representations in such a nice way that you can quite efficiently work out these multiplicities. So if it's the type A root system, these C lambda mu news are kind of much older and well known. These are called the Littlewood-Richardson coefficients. And there's a big there's a big history behind them. You can get them by counting various sorts of tableau. But actually, once you have the theory of crystals in place, you can work out that combinatorics of tableau that's older kind of quite naturally. And so this theory of crystals, this is way off what we're going to do. Kashiwara discovered it by thinking about quantized enveloping algebras. These things, UQ of G, which are some deformations of the universal enveloping algebras of semisimple Lie algebras. And it's a whole beautiful story, which would be a whole separate course in Lie theory on quantum groups and crystal bases. Okay, so that's just a little tiny glimpse of representation theory. It's a remarkably rich and wonderful subject with all sorts of different points of view and different techniques, algebraic geometry to combinatorics.